Good morning, everyone. Welcome to this week's HSMA training. And again, today we are continuing our journeys through the fascinating world of machine learning. So we began a few weeks ago by introducing some of the core concepts of machine learning. We then started to look at logistic regression as being a simple but often effective way of trying to train a machine to automatically classify or predict various outputs. We also explored some of the important ethical issues that can arise, particularly around machine learning applications. And then last week, Sammi took you through some other machine learning approaches looking at tree-based models and showed how these kinds of models were really, really effective. And you may recall one of the slides that Sammi showed that these kind of approaches were kind of like the second most popular in the world of machine learning. This week we get on to the number one, which isn't necessarily to say that this should be your first choice. And we'll come on to that a little bit more. But there is no denying that the world of deep learning and neural networks have kind of taken over AI with good reason in a lot of cases. These are enormously powerful tools that have transformed what AI can do in the modern world. And so this morning we're going to be talking about these kind of approaches, and we're going to be spending quite a lot of time trying to get our heads around what neural networks are and how they work. And I will flag up right now, for those that didn't see the conversation on Slack, I was first taught neural networks many moons ago when I did my undergrad degree, and I absolutely hated them. I did not understand them at all, and vowed I would never look at neural networks again. And it was actually my colleague Mike that convinced me to give them a second chance. Certainly with the benefit that they are much easier to use now than they used to be. Certainly when I learned them, but even then, that was sort of much improved over what they were many years ago. But I did give them a second chance, and now I understand them and I teach them, and I'm very fond of neural networks and very passionate about what they can do. So I want to flag that up first as a kind of a bit of a personal example of how, don't be too hard on yourself if you don't understand either this or anything in the course the first time around. We are not all experts in everything, so that's kind of worth flagging up. And sometimes it takes time for this stuff to get in. And in my case, it took the best part of 10-15 years for me to fully understand neural networks. But the second thing to say is that hopefully that has come across in my training and the way in which I try to teach these, coming from a place in which I did not understand them the first time around. So hopefully, I'm hoping that the way I teach it will help you to try and link up the important concepts in machine learning a little bit more quickly than I did. And to the very least, to appreciate that these are hugely important and powerful things. But as ever, going back to what we said earlier in the machine learning module, you should always start really with simpler models. Neural networks are not simple models, and they are computationally expensive, and we'll come on to that more in a moment. But they can be very powerful. So it's always worth starting with some of the simpler stuff that we've looked at so far, but then see if your model, your problem would benefit from a deep learning approach. Okay, so let's start talking about neural networks. And first of all, I'm going to once again thank my colleague Mike for developing a lot of the content, and really, to be honest, pushing our team into being experts in kind of applied machine learning. Mike was the driving force behind a lot of that. And so, once again, a plug for the Titanic Machine Learning book that he has that underpins many of the exercises that are scattered throughout this entire module. So, do have a look at that if you haven't already. Okay, so let's start talking about neural networks. So, what are neural networks? More specifically, we should probably technically refer to them as artificial neural networks, or ANNs, but because that kind of refers to the kind of neural network that we're talking about. But these days, very few people will say artificial neural networks, and mostly when people talk of neural networks, they refer to the things that we are talking about here. They are basically networks, clues in the name, of neurons, which are kind of nodes, with various connections between those neurons and signals that are sent along those connections. And basically, they were first designed to try and mimic the way in which the human brain works. So, which kind of makes sense if we think about it. If we're trying to develop some artificial intelligence, some way of recreating intelligence digitally within a computer, then perhaps, looking at the way in which we have the human brain, which is obviously a very powerful learning mechanism, looking at the way in which that works and trying to replicate that seems to be a pretty sound idea for trying to create artificial intelligence. But they were primarily designed really so we could try and get a better understanding of how the human brain works, which is still very much in many ways a mystery to us. And one of the great ironies really of the development of neural networks, as I touched on before, is that whilst they have shown to be much like the human brain, extremely strong learners, very, very powerful for a lot of applications, learning applications, it turns out we still don't really understand why they work. And you'll see a bit of why that is as I explain this throughout the morning, and why they are considered very much a kind of black box modelling approach. Now, there is a growing field of explainable AI, which Sammi's going to be going through and touching on this afternoon, which is helping us to try and unpick some of the outputs from some of these more black box approaches like neural networks. But even with that, we still don't fundamentally understand some of the concepts and how they work at a very detailed level in a neural network. So we have to kind of pretend it's magic a little bit, but we do know that they are very powerful learners, and we understand the basic structure, and it turns out they're exceptional for a lot of applications. Now, if you're going to sort of go in deep with neural networks, you might find that you may want to, or particularly if you get into extremely big problems to try to tackle with neural networks, that want may turn into need. You may end up considering getting a GPU. So GPU, for those who don't know, is just a graphical processing unit, and primarily designed for gaming purposes and for high-end video and graphics editing. But it turns out that the things that make them good for that actually make them exceptionally good for neural networks in particular, because that for gaming and for video and graphics editing, basically what you need is something that can take huge amounts of information all at once and process it very, very quickly all at the same time. And that's essentially what your GPU is doing when you're sort of playing games or editing videos. But as you'll see, as we talk about the neural networks, that's exactly the kind of thing that you need to happen when you process a neural network. Now, that's not to say they're always the best choice. There is a limitation to them as well. Whilst they can process very quickly and in parallel, it does take time to load all of that vast amount of information onto and off of the GPU. So they make a lot of sense where you've got very, very big problems where that initial cost of loading the information onto and then getting it off the other end is far outweighed by the processing speed advantage that you get. So if you are convinced by that and you do want to at some point explore getting your own GPU, here's some things to note. You'll need to make sure that it's an NVIDIA GPU. Unfortunately, AMD stuff doesn't really work for this. You have to ensure it's CUDA enabled. So CUDA just as an abbreviation stands for Compute Unified Device Architecture. These are basically the GPU's equivalents of your kind of processor cores that you have in your computer, and they're the bits that do the magic that we need, the parallel processing bit. Not all GPUs have them, not even all NVIDIA GPUs have them, so you have to make sure that it is CUDA enabled. And probably most importantly of all, you have to have pretty deep pockets, because these things are, particularly if you look at the high-end ones, are not cheap. We are talking thousands of pounds for a high-end GPU. So either you have to have pretty deep pockets or can sweet talk your IT department, which, by the way, is exactly what I did. So this is my rig here. It's what was at the time a £5,000 PC. Half of that was for the GPU, which is a 4090 with 24 gig of RAM, and was high end in terms of the processor and the main memory, the 64 gigabytes, and all that kind of stuff. And of course, the swishy lights as well. You can't put a price on swishy lights, but that was a very expensive computer, and I don't know if it was a coincidence that the entire university's policy on purchasing computers changed shortly after I managed to convince the department I did need a computer with that was £5,000 and with swishy lights. I'm sure it was just a coincidence. But anyway, perhaps that's an extreme example, but in some cases you might be able to, and we have had instances in the past where people have managed to get their IT department to give them some kind of GPU capability, and it doesn't have to be as extreme as getting a 4090. There are cheaper alternatives that will get you a lot of advantage as well if you are getting deep into deep learning. There are also alternatives if you do want to go down that road, and it's not practical for you to buy your own CUDA enabled GPU, or you're not going to be able to convince your IT department of that. There are online services, so Google Colab allows you, as we saw right back at the start of the course, you can use both a GPU and also a TPU in the cloud. Bear in mind, if you're on the free tier, obviously there are priority restrictions, but you can do that and you can access that kind of thing. And also, for simpler models, it's far less essential. You may well find for the kind of things that you're doing in your projects, for example, that you don't need that kind of power. And you might just have the patience to say, okay, well, I'm going to have to leave this thing running for a few days, but that's the price that we have to pay. And that's okay too. Just to flag up, the examples you'll be looking at this morning and throughout the course are all designed so that they should be tolerable on your computers. But I will flag up that this is the point at which you may start to notice, if you've got a particularly slow computer, that some of the exercises are taking a little bit longer to run than you would like. So my advice, particularly for this morning's session, and this will apply for some of the natural language processing stuff that's based around neural networks when we get into module 5. If you've got someone in your group or some people in your group that have not quite so terribly slow computers, it might be worth getting them to lead on some of this stuff. Otherwise, you could end up spending a lot of your time staring at a progress bar. So it should be fine. To give you an idea, in the notebook that you're looking at this morning, it tells you how long it took to run on mine, and then you can kind of benchmark how far off you are. Bear in mind, mine's incredibly quick because it cost £5,000. So, but hopefully it'll give you an idea of whether your progress bar is actually going to finish in time. Okay, so that's just a little aside. It's worth flagging though, because if you do want to get serious about big problems that are so well suited to neural networks, and you really want to go deep into this, then you may need to think about some form of investment either in local hardware or in potentially paying for some cloud compute software. Capabilities, I should say. Okay, so let's start talking about the structure of a neural network. And I said that neural networks are basically networks of neurons. So let's start by talking about the neuron, which is kind of the basic building block of a neural network. Now, these neurons originally were named perceptrons in the very first artificial neural networks. And basically the idea of these neurons is that they each perform a very, very simple task. All they do is take all of the inputs that it gets, multiplied by each input multiplied by a weight that represents the strength of that input's connection to that neuron. Then it adds up all of those numbers and then spits them out the other side according to some kind of what we call an activation function. And basically the activation function just takes that raw weighted sum and converts it in some way, and we'll look at more about that in a moment. But at a fundamental level, that's all a neuron is doing. It's got some inputs coming into it that are connected along these connections. There are weights for each of those connections, and it says, okay, that multiplied by that, plus that multiplied by that, plus that multiplied by that, plus that multiplied by that, adds it all up, and then the activation function transforms it in some way, and then it spits out the other side. That's basically all a neuron is doing. Okay. Now, the neuron, or perceptron, as it was originally called, was first conceived by the American psychologist Frank Rosenblatt in 1957. He was basically, as I say, trying to simulate the workings of the human brain with the idea of trying to create this very early form of machine learning in which a computer machine tried to learn via trial and error. So let's look at this in a bit more detail. As I said, we've got the neuron that's basically accepting these inputs. Now, these inputs here kind of represent, and it'll get a bit more complex in a moment, but for now, let's think about these inputs as representing our features. That's, remember that they're just basically the data in our columns in our data, the information from which we are trying to make a prediction. And so these are the inputs into that neuron. And as well as those things, we also have this thing known as the bias, which is one of our inputs. Now, the bias is a little bit like a constant in a linear function. It basically, what it allows us to do, or what it allows the neural network to do, is to say, okay, I think I've got a good representation of what the inherent patterns are in this data. But actually, if I just shift this graph over to the left a bit or over to the right a bit, it'll function better. That's basically what the bias is. and you don't have to particularly worry about the bias. Particularly using the software that we're going to be using, the network will do everything for you. You don't even need to worry about including it. All of that is done for you, and the network will deal with it automatically. It treats this as a separate input, and it plays around with it to try and get things as good as they can be. So you don't need to specifically worry about the bias, but it's worth knowing that it's there. Okay, so we've got our inputs that are feeding into our neuron, and each of the ways in which they are connected into the neuron are along these connections, and each connection has an associated weight. And that weight is just basically a number that represents, at this stage, at the single neuron stage, essentially the importance of that particular input to the final calculation. So if we just had a single neuron model, then this would essentially be the weight of each feature, because that's our feature data, that's the weight of it, and then these weights would essentially represent how important these features are. Now, you'll see in a moment why it's a bit more complicated than that. But strictly speaking, the weights represent the relative importance of this input to this neuron. In other words, how strongly is this input going to feature in this calculation, which kind of makes sense, because basically they're being multiplied by the weights and then added up and then spat out with an activation function. And basically what the network will do is it will play around with these weights in order to try and improve the quality of its learning. And that's basically the tool it's going to use. It's going to play around with these weights and see if it can get better predictions by playing around with them. And at the start, it may surprise you to learn that a neural network starts with completely random weights. They are completely random numbers, okay? And then it learns from there. And you might find that quite surprising, particularly as they turn out to be such powerful learners, but it does start completely at random. So you've got your inputs, each connected to the neuron via a weight. These start at random, and then the machine gradually plays around with them and adjusts them. They all feed into this into the neuron, which performs a weighted sum. So it just says this multiplied by this plus this multiplied by this, etc., adds it all up. And then once it's done its weighted sum, it fires it out the other side via an activation function. And the activation function, as I say, is just transforming that output, that weighted sum, in some way. And we'll come back to that more in a moment. And then we have this concept of error. Error, or loss, as it's known in machine learning, as we saw last week, is basically how much was this output from the neuron right or wrong. And basically the learning of a neural network is all to do with looking at how wrong you are and then adjusting these weights to try and be less wrong the next time. That's basically how a neural network learns. So I said that the activation function spits out an output, which is basically just this weighted sum that's fed through the activation function, so it transforms it in some way. And then coming out the other side, you will have this output, and that output might represent a prediction. If you're doing a pure regression problem where you're essentially just trying to predict house price or something like that, or indeed for a classification problem, which, as I say, is probably the most likely kind of problem you're going to be looking at for your kind of issues, then it'll likely be a number between 0 and 1, which will determine the classification, as we've so far seen with the other methods. So you'd have, is it above our threshold of 0.5? If it is, then it's class 1. If it's not, then we call it class 0. But as I say, the key to how the neural network learns is via the error. And essentially what it's trying to do is adjust these weights so that the error lessens over time. So let's consider a very, very highly simplified example of a single neuron doing its thing. And we're imagining a single neural network which won't exist in the real world, but just to show you how this thing works at a very fundamental level. Also worth flagging up that as well as this being highly simplified, the inputs that we're putting in here would actually be subject to feature scaling, as we talked about, and it would actually be min-max normalized. If you remember, neural networks are normal, we said was the mantra when we looked at normalization and standardization a few weeks back. So to make sure they're all on the same scale, these wouldn't actually be the raw numbers that we would end up using. They'd all be between 0 and 1 in reality. And also in reality, and we'll come back to it later, they wouldn't look like this. They would be in a weird kind of shape that you've not seen before. But again, we'll come back to that, and don't worry too much about that. But at a fundamental level, just to help you understand what a neuron is effectively doing, to try and unpick these neural networks, understand, actually they're processing some quite simple stuff once you zoom right in. Then essentially here we've got our neuron, we've got 4 features plus our bias, and the bias is set to 1 basically, and then the neural network just plays around with the weight. So we've got a number of emissions is 3, age is 20, previous length of stay is 5, distance to the hospital in miles is 9. Again, these would be normalized in a real neural network. And then we've got some completely random weights at the start. And so all the neuron is doing is saying, okay, well, that's 1 times 2 plus 3 times 0.7 plus 20 times 1.8, etc., etc. That comes to 97.2. Then it's gives it over to a activation function. In this case, we're just using a step function, which you will never use anymore in reality. We'll come on to that. And a step function basically just says, okay, well, if it's above a number, make it this. If it's below a number, make it this. So here our step function says if it's greater than 50, make it 1. If it's less than 50, make it 0. It's kind of what you were doing in the Dan's Desert Island DVDs exercise. So here we get an output of 1 because it's 97.2. But it turns out the real output is 0. So we're very wrong. So we go back and or the network goes back and it adjusts the weights. And then it's changed some of the weights here. And then this time the weighted sum gets to 28 and it matches the real output. That's a highly simplified example, but fundamentally that's kind of what's going on at a very, very low level. Now, of course, that might sound fairly straightforward, and indeed in some ways it is. And this we found here in our example, this works exceptionally well. These combination of weights work really well for this data, but of course the neural network is not just having to do it for this data. It needs to learn how to adjust the weights so that any data that comes in, it is right most of the time. And that's a much harder ask. And it's also much harder because, of course, we're not dealing with just one neuron, because what we're actually dealing with in a neural network is lots of neurons all connected together. And that's basically what a neural network is. It's a collection, a network of neurons that are connected together. Each of those neurons, each of these individual circles here, they're just doing what we were talking about a moment ago. And these neurons are connected together across various different layers. So they're clustered together in layers. And basically the outputs from neurons in one layer feed into the neurons of the next layer. So the outputs from these neurons act as the inputs to these neurons. And eventually we get through to a final layer here. Now, a fully connected neural network is one in which every neuron in one layer is connected to every neuron in the next layer. So this is an example of a fully connected neural network. This neuron here is connected to all of these, so is that one, so is that one. And the same here, this one is connected to all 4 of those, so's that one, so's that one, so's that one, etc. That's known as a fully connected neural network. And every connection that we see here has its own associated weight, just as we saw with the single neuron example. And basically what the network is trying to do is to learn how to adjust all of those weights across all of those connections so that it predicts by the time it gets to this final bit here, it comes out with the right answer most of the time. Okay, that's why it's a little bit more complex, and you can probably already see that this is a little bit of why they are a bit more black box, because if we were just dealing with a single neuron, as we said, we can imagine our feature data coming in, that represents length of stay or whatever. And so the weight of length of stay represents the importance of length of stay to our prediction. What does that weight mean there? What that weight means in reality is that is the strength of the connection between that neuron and that neuron. So by the time, here's our inputs, by the time it's been fed through sometimes hundreds of layers in some cases, although rare, we're usually looking, sort of between 3 and 10 layers for a typical neural network. What on earth does it mean in that spaghetti in the middle? What does a weight really mean? It doesn't any longer, we can't just simply say it represents the importance of length of stay to our prediction. It's a jumble. And essentially the neural network is having to do this very difficult job of saying, okay, given this set of numbers that you're giving me here, you want me to get to the number 1. So I need to adjust all of these weights so that I get to the number 1, but then when you give me this set of numbers, I need to get to the number 0 with the same weights. Okay, so that's why it's a complex problem, because it's basically having to try and work out which weights along these connections, which then apply to these weighted sums, will get you to the right answer most of the time for whatever inputs you pass in. And that's the magic of a neural network. And these multiple layers of a neural network basically are the thing that give the name to the subfield of AI in which neural networks live, and that is deep learning. So if you hear the term deep learning, that is what we mean. It is the neural networks, basically this idea of having neurons connected across multiple layers. So these various different layers, let's have a look at them in a bit more detail. So we always have an input layer here. So the input layer is basically the first layer of the network, and that takes our input data that will be scaled. Remember, we have to feature scale our data to make sure all of our input data is on the same scale. And for a neural network, that's likely going to be normalized. When we looked at logistic regression, we standardize the data, which remember is where you say you put everything with a mean of 0 and a standard deviation of 1. Here we're going to normalize, which is basically make everything between 0 and 1. That's we typically do that for a neural network. It's important to note there is no activation function used on the input layer. The input values are just passed out as is. Okay. Then we're looking at the other end of the spectrum. We've got the output layer, which is our kind of final layer of the network. In a classification type problem, which is the kind of problem, as I say, that you are most likely going to be looking at, and most of the type of problems that we cover on the course, that final layer essentially represents a prediction as to whether an example belongs to a particular class, where your output is basically a value between 0 and 1. Whether it falls above or below a threshold determines whether it belongs to class 0 or class 1, and the default is that threshold is 0.5. Now, for a classification problem, you typically have a single neuron as your output layer, and that's the one that will spit out the number between 0 and 1. But it can be more than one as well, even for a classification problem. So you might have, for example, a problem where you've got an image recognition classification problem. You're trying to classify an image, and so essentially you have pixel data that gets fed through here, and you want more than one output neuron in your output layer. because you might have, for example, three different potential classes. You might have, is it a flower? Three different types of flower, and then each of those neurons would give a kind of likelihood that it is that kind of flower. So you can have more than one neuron in an output layer. Also worth flagging as well for regression problems, which remember is where you're predicting a continuous value. So you're not trying to predict a class, you're trying to predict a value itself. The output's typically left raw because that's the output we're trying to predict. Whereas we do a conversion to convert to something that resembles a probability when we do classification problems, and we'll talk more about that in a moment. So that's an output layer. We've got our input layer we've talked about, and then basically the hidden layers are the layers in the middle. So there's everything else, the stuff in the middle, and this is where the real magic happens. This is the central brain bit of a neural network. Okay, so we've talked about activation functions, and we've said that an activation function is basically just something that the weighted sum of a neuron is passed to the activation function, and the activation function transforms it in some way. Now, there are lots of different activation functions, and you can have, if you so choose, different activation functions for every neuron in your network. Do not do that. That is not what is typically done, and you won't have a very easy to train network if you do that. Most of the time, you will have one single activation function that you use across your network, with probably a different one, if it's a classification problem, a different one used for your output neuron or neurons. But typically, for most of the network, you will use the same activation function. So just to have a little look at some of the most common ones. As I say, there are lots and lots of different ones out there. Let's have a look at some of the common ones, not necessarily the ones that are commonly used, but also some of the ones that are important to flag up for historical reasons. So the first one to start with is the linear activation function, which is the most boring activation function in the world, because it basically just doesn't do anything at all. It just passes the weighted sum through exactly as is. So linear is often used as the activation function for an output layer neuron for a regression problem. So remember, with a regression problem, you're trying to predict a value, and it's the value that's of interest, not a class. So if you're trying to predict a continuous number like a house price, you typically use something like a linear activation function to leave it raw, basically. So that the number that comes jumbled through that network, through its maze of weighted sums, that's the number you want as your prediction. The step activation function is the one we just looked at in our simplified example a moment ago. That says basically if it's above a threshold, output 1. If it's below it, output 0. It's never used now, other than in demonstrating simplified examples like that. It's a historical artifact, but it is important because it was the very first activation function. But as I say, it is nothing more than a historical artifact, like my jokes. Sigmoid. Now, sigmoid is a far more useful one for a lot of the things that you're going to be doing. So sigmoid basically scales an output to between 0 and 1 using the logistic function. We saw an example of the sigmoid function in the logistic regression session. Sigmoid is good for producing probabilities, and therefore, as you might expect, if you've got a classification type problem, which, as I say, is most of the kind of problems you'll be looking at, then a sigmoid activation function is usually the activation function you will use for the final output in your network, because you're after a probability, and the nearer it is to 1, the more confident you are it belongs to class 1. Also flagging up tan H, so that's similar to sigmoid, but it scales between -1 and 1 rather than between 0 and 1. Used to be quite common in older networks, but doesn't tend to be used much now, but worth flagging up. One that is worth flagging up, though, is ReLU. ReLU stands for Rectifying Linear Unit. Now, this one's really interesting. So ReLU, basically, all it does... So remember, all an activation function is doing is just taking the weighted sum and doing something to it. All a ReLU activation function does is say if the output of that weighted sum is a positive number, then just keep it as is. So work exactly like the linear activation function. But if the number is negative, then make it 0. That's all it's doing. It's incredibly simple. But it turns out that ridiculously simple activation function allows us to model non-linear functions and sufficiently capture non-linearity in our real-world applications. So you can actually learn very complex patterns just by doing this really stupidly simple thing of saying if the number is positive, just use the number. If it's negative, make it 0. That turns out to be one of the most powerful activation functions you can use, and it's enough to make it non-linear, and is probably the activation function you will use the most. Okay. It is also worth flagging up, though, there is something known as leaky ReLU, which is basically works exactly the same as ReLU, but rather than converting all of the negative numbers to 0, it basically reduces their scale. So if it's negative, it doesn't make it 0, but it makes it far less important, if you like. So it's not quite 0, but it makes it it's diminished. The number is diminished. So it allows us still to have negative numbers floating around the network, but it compresses the range of numbers, basically. Now, leaky ReLU is particularly useful if it turns out that the weights in your network are frequently being set to negative values, and that can happen if you've got high learning rates. And we'll talk more about learning rates in a bit. Basically, where your weights are commonly being set to negative values, if we use ReLU, then remember a negative. The more weights that you've got that are negative values, the more likely it is that the output of a weighted sum that includes those weights is going to be negative itself, and that means that essentially the output from that neuron will be 0. So ReLU will spit out 0 more and more, and it effectively switches off that neuron, because that neuron has outputted nothing. It's just outputted literally the value 0. And this can be a problem. It can lead to something known as the dying ReLU problem, which is where your network basically increasingly shuts down because it's learning too fast. There are too many weights that are being set to negative values. Negative values are increasing the likelihood that ReLU spits out a 0, which effectively shuts down the neuron, and that effect can snowball such that you can even reach a state where your entire neural network dies because all the neurons are dead. They're all just spitting out the number 0. And that's known as the dying ReLU problem. And if you want to read more about the dying ReLU problem, which is a fascinating concept, there's a really nice, simple explanation of the dying ReLU problem this link on towards data science. So leaky ReLU basically tries to avoid that, because you haven't got this thing that every negative number is set to 0. It's set to something closer to 0, but it's not quite 0, so you don't have that shutdown effect that can happen. So there's a lot of activation functions I've talked about there, and indeed there are many more that I have not talked about. But generally, for classification type problems, really most of you would start with ReLU activation functions for your hidden layers, that's the ones in the middle, remember, and sigmoid for your output layer. Remember, that converts it to a probability, converts it to between 0 and 1. You might want to consider switching ReLU for leaky ReLU if you encounter this dying ReLU problem, and you might want to consider switching the sigmoid activation function on your output layer to something known as softmax if you've got multiple outputs and you want them to add up to one. So you might have a number of outputs and say that you want the probability that this is a dog, the probability that this is a cat, the probability that this is a fish, etc. And they need to add up to one. So you can use something called softmax if you've got that kind of problem. But to be honest, most of the time, ReLU in the middle, sigmoid at the end will see you well. Okay, so let's talk about some concepts now that are hugely important to neural networks, known as loss and backpropagation. So we've already talked a little bit about loss. Loss is basically just error. But the magic of a neural network is basically the way in which it adapts the weights of the connections within that network over time. And the way in which it does this is it uses a process known as backpropagation. And backpropagation distributes the error or loss. Remember, that's all loss is. And loss just represents basically how far off the neural network's output was to the correct answer. The backpropagation distributes that loss across the network. So basically, it works out which bits of your network are to blame for getting it wrong. And it will then use something else, which we'll talk about in a moment, to adjust the weights to try and rectify that. So it's kind of looking at what's gone wrong, where it's gone wrong, and which kind of connections and weights were most to blame for getting things wrong. Now, in order to do that, it needs to work out what the loss is, what the error is, and to do that, we need to something known as a loss function, which will calculate the error, and we also need a way to distribute the error, which is our backpropagation method. There are various ways of measuring loss, various loss functions, and also various ways of optimizing the backpropagation algorithm. So let's have a little look at some of these things now. So let's start with loss functions. These are ways in which we can try to calculate our loss, our error. The two most commonly used loss functions these days for neural networks are mean squared error loss and cross entropy loss. Mean squared error loss is basically typically used for regression problems, so where you're trying to predict a value rather than a classification. And basically it just works out, as we saw a little bit of when Sammi covered this last week, it takes calculates the difference between each observed or real value and the predicted value and squares it. So if we've got our real length of stay as 20 days, but it predicted that it was 16 days, then the squared error would be 20 minus 16 squared, which is 16. And it then calculates a mean squared error loss, calculates the mean of those squared errors across the data by basically just adding them all up and then dividing them by the number of data points. It's actually not doing anything particularly complex. The reason we square the error is because the error could be on either side of the correct answer. So in other words, here the real length of stay is 20 days. Here we predicted it was 16, so we were 4 under, but we might have equally said that it's 24 days and we'd been 4 over. A mean squared error loss would treat that identically. So the scale of the error is 4. Regardless of whether you are above or below, it treats the scale of the error in the same way. So that's usually used for regression type problems. Classification type problems, however, you tend to use cross entropy loss. And cross entropy loss is basically mostly, as they use for classification networks, and a binary cross entropy loss is probably the loss function you will use the most, because you use binary cross entropy loss, as you might guess from the name, when there are 2 possibilities, 2 classes, survived or died on the Titanic, for example, treated, not treated in the stroke data. And many of your networks are likely to be binary classification type problems, and so you will likely mostly use binary cross entropy loss functions. Now, the way in which binary cross-entropy loss, or cross-entropy loss in general, is calculated is actually quite complicated, and you'll be pleased that I'm not going to go into the details of how it does, because it is complicated. But essentially what it does is it assigns penalties, and those penalties increase the further away the prediction is from the true probability. So that basically means if a prediction is confident but wrong, then it would suffer a huge penalty. So if you had an output of 0.9, in other words, that was a confident prediction that it's class 1, when actually it's a class 0, it'll get a massive penalty for that, compared to something like a prediction of 0.55 when the true class is 0, which is a kind of a marginal prediction that it's class 1, but it was quite near to being on the fence. That will get a much less of a penalty in a cross-entropy loss function than something that is confidently wrong. So that's loss functions, and basically, as I say, most of the time you're going to be using binary cross-entropy loss for your loss function. So backpropagation is the thing that is looking at how you distribute that loss, that error, back throughout the network, in order to work out how much blame to put on various bits of the network. And really, this is the magical part of a neural network. This is the thing that it turns out has transformed the way in which neural networks work and makes them so powerful. It was actually conceived in 1986 by the computer scientist Geoffrey Hinton, and it absolutely revolutionized the way neural networks work, because it allowed neural networks to be able to train well. Now, it's probably not a great surprise that the mathematics behind backpropagation are incredibly complicated, and I am not even going to attempt to try and explain them to you. It should not be a great surprise, really, that they're that complicated. Let's not forget, it took nearly 30 years from the invention of neural networks in 1957 to Geoff Hinton coming up with this in 1986 to actually come up with this thing that actually made them work properly. So, you know, if it takes a very clever man 30 years, let's assume that we're not going to attempt it in 10 minutes here in HSMA. The good news is you do not need to understand the mathematics behind how it works. You just need to understand what backpropagation is doing at a general level. And the nice easy way to think about it, I always think of it as your blame assignment algorithm. It's basically saying, okay, we were wrong by this much. Who was responsible for that in this network? And the backpropagation algorithm will use something known as an optimizer to update the weights in the network, because once it's worked out who's to blame, it needs to do its magic of saying, well, okay, we need to change the weights, because that's the way in which it tries to learn and improve, so that we're better next time. So let's talk a little bit about optimizers. Basically, an optimizer decides how to adjust each weight, both in terms of by how much, so the magnitude, and also the direction, so to increase it or decrease it, within the network based on the loss, the error that has been backpropagated. And of course, the idea is that the optimization algorithm is trying to adjust the weights so that it is less wrong the next time the loss, the error, is reduced. So the optimizer is kind of the correction algorithm. If backpropagation is blame assignment, the optimizer is the correction algorithm that will go in and fiddle around with the weights to try and improve things. Now, as a builder of a neural network, it's your job to work out which optimizer you are going to use, and it will probably come as no surprise that there are, of course, lots of different optimizers too. I'm just going to cover 3 of the main ones that are commonly used, very, very briefly, just for the benefit of time. But the first one is called stochastic gradient descent. Stochastic gradient descent is basically, so it's a classic optimizer. This is one that's been used many, many times over the years, basically adjusts its weights in response to how much changes to those weights affect the output. So how sensitive is the output to changes to those weights? And basically, it will make bigger changes to the value of a weight the further away it believes it is from the optimum value, and it works out or it predicts how far away it is from an optimum by looking at that sensitivity. How sensitive are the outputs to a weight adjustment? So if it finds that the output, if you make a small adjustment to the weight and the output changes radically, then it reckons that it's further away from the optimum, from a good place to be. And then it gradually makes smaller changes to a weight when the output becomes less sensitive to adjustments. And a nice way to think about it here is to think about this as being, these are our weight values on the x-axis. This is our loss, our error. So we want low is good. We want to find the weights that give us the lowest error. So whilst we're maybe over here, the stochastic gradient descent will be making faster changes because we're on a high gradient. So a small change in weight leads to quite a difference in outcome, but it will gradually slow down as that gradient becomes less steep. Because changes to the weight are leading to smaller changes in terms of our loss. Now, you might identify that there is a particular problem with stochastic gradient descent, and indeed a lot of optimization algorithms, in that by using this approach, by making really big changes when you're further away and then smaller changes as it thinks it's getting closer to a better answer, what you can end up with is an algorithm that gets you stuck in what's known as a local optimum, and it misses the global optimum, i.e. what's the best configuration, the optimal configuration for these weights that will give you the best performance, the lowest error, and instead it misses that and it finds a local optimum. So if you imagine, this is just, again, highly simplified, but this is our global optimum. This is the point at which this combination of weights would lead to the lowest error and therefore the highest performance from our model. But a stochastic gradient descent, depending on where it starts, which remember is completely random with the weights, could end up stuck here or here, because it'll if it starts, say, here, it'll gradually it'll go faster and faster, and then it'll slow down the changes to those weights, and it'll get trapped here, and it may not get out the other side because things will be getting worse, so it gets trapped. Now there is a fix for that, and you can use something called momentum, and that basically gets the algorithm to try and explore a bit more and try and prevent it getting stuck in one of these local optima. Nice way to think about momentum, I think, is think about momentum as kind of giving it a bit of a shove. So if it's stuck down here, you're kind of giving it a bit of a shove, so it ends up, woo, it's gone over here now, and maybe it'll find something better. And indeed, in this case, it would. So that's one approach, one optimizer. Another optimizer is known as RMS prop, which stands for root mean squared propagation. Again, another classic optimizer for neural networks. Quite similar to the way in which gradient descent works, but it's basically got a dynamic learning rate. So basically the amount that a weight changes varies for different parameters at different times, depending on the rates of change being observed. Again, you don't have to worry too much about it, but it's kind of a variant of gradient descent, stochastic gradient descent. The third one I want to talk about, though, is Adam. Adam is probably the most commonly used optimizer today. Mike always says, if in doubt, use Adam. It's a good mantra to use. Most of your neural networks, you will probably use Adam as your optimizer. It basically combines the benefits of RMS prop with another extension of gradient descent called ADAGRAD, which stands for Adaptive Gradient Algorithm, and it basically it's kind of a best of all worlds amalgam of these really classic optimization algorithms that adjust in ever more sophisticated ways the way in which your learning rates adapt. Now, again, I don't want to get into the complex mathematics behind this. So to summarize optimizers, your best bet's probably to use Adam. You might want to try RMS prop to see how performance compares. And stochastic gradient descent, you don't tend to use that now, but the core concepts that made it such a classic have passed on down to these other optimizers, which you do tend to use. So let's just pause for a little summary, because that's a lot of information you've taken in so far. So we have activation functions that are the things that transform our weighted sum in our neuron. And for a binary classification problem, which is most of what you'll be doing, you typically use a sigmoid activation function for your output neuron, and ReLU or maybe leaky ReLU if you run into the dying neuron problem for your hidden layers. Loss functions basically just calculate the error that the network has made, and if you've got a binary classification problem, you typically use a binary cross-entropy loss function. Backpropagation is your blame assignment algorithm. It works out which neurons are to blame for the error and by how much. And then your backpropagation will use an optimizer that is the thing that's going to try and fix it. So they will work out how to adjust the weights in your network to try and make things better the next time. And if in doubt, use Adam as your optimizer. So activation functions basically say, here's my answer. Loss function says, but we're wrong by this much. Backpropagation says, right, which of you's responsible in this network? And then the optimizer says, right, I'll go in and fix things. I'll adjust you by this much. Let's try it again. Here's a fluffy cat, because I realise that's a lot of information to take in, and your brains are probably slightly melting from all that information. Of course, I can't show a fluffy cat without showing my own fluffy cat, who will refuse to be upstaged by a kitten. So whilst we gaze lovingly at this photo of Prince, I'm going to pause for a moment and say, Sammi, are there any questions so far?
Yeah, not too many. So we've got one which I think may have been slightly answered by your summary slide on how do we decide which activation function to use. There's a nice answer from Lewis around potentially bringing in a bit of domain-specific knowledge sometimes because you're using an off-the-shelf architecture, maybe a bit of hyperparameter tuning, but also just as you've got on your summary slide, that's it. Well, what you've got on your summary slide is a good place to start, but anything to add to that?
No, I think it's with all machine learning, but particularly I think with neural networks. I keep saying this is an art form, and it really is. There are no right answers. So I can say to you that a good place to start is using an Adam optimizer and using a binary cross entropy loss function and using ReLU as your activation function for your hidden layers. And that probably will be the case. But that also shouldn't stop you exploring other things as well. And it may turn out that you've got a problem that ReLU isn't the best activation function. You get better performance from something else. A lot of neural networks is exploring different things, trying different things. They are magical black boxes, and because of that, there aren't hard and fast rules. There are things that sort of general rules of thumb are things to probably default with to start with that have been shown to work well for particular kinds of problems, which is kind of what I'm conveying to you here. But that doesn't preclude you from exploring other things.
Fantastic. Somewhat related to that, how would you spot if you've encountered the dying ReLU problem?
That's a good point. I will get back to you on that. I thought somebody was going to ask that, and I should have looked up the answer. I believe I've looked this up before, and I'll get back to you. We'll have a look at that for you.
Thank you. And the only other question is kind of more of a how important is it to know and understand the mathematics behind algorithms for becoming a good data scientist?
I would argue, from a perspective of somebody that does not understand the mathematics, behind the algorithms, I'm going to say with that completely unbiased opinion, it's not important at all. I think all you need to understand is the general sense of what it is doing. I certainly do not believe that you should be going out and trying to work out the mathematics behind neural networks. You will get a headache if you do. They are incredibly complicated at a mathematical level, and probably part of the reason that I was put off neural networks for 15 years, because as a computer scientist back then, we were taught some of those mathematics, and I did not like that. So I am not a mathematician in that sense. I try to avoid the mathematics. I try to condense it down to, okay, well, I need to understand essentially what this algorithm is doing. So if you can understand that backpropagation is essentially working out how to assign blame across a neural network, that is sufficient for you to understand and build a neural network. You do not. There are tools out there. You never have to worry. If I never mentioned backpropagation, you could have gone on and built a neural network without worrying about it. But I think it's important you know how that works, so you can understand a little bit of how these things come to be. Because some of the things you need to understand in general terms when you're making decisions about how to design and build them. But no, the mathematics, I would argue, you do not need to understand them.
Fantastic. And yeah, I think I would echo the same. I think you can become a very safe and effective user of all of the things we teach you on the course without having to fully understand mathematics. There's lots of people working on the mathematics out there who are going on and developing new and incremental improvements or new methods, but actually to use this in your day to day, it's more important that you understand fundamentally how it's working. So yeah, exactly as you've said there. So fantastic. I don't think that there's anything else. So onwards past, although it's fabulous to see prints. So
It
we
is,
could
yeah.
just stay here.
We should just leave this slide up, I think, for the rest of the day. I should have just committed the rest to memory, and we can just stare at prints whilst I talk
Yeah.
about the rest. I'm just going to see how many slides we've got left. I think it's only there's not too many more, so we will take a break. So I apologize. I've run slightly over, but there's lots of time for the exercise, more than you probably need, and plenty of time to have a break. So we will plough on with these final bits, and then I'll sort of set you free. Let's talk a little bit now about iterations and epochs. When we train a neural network, we have basically what are known as multiple iterations. And basically, in each iteration, we pass through a batch of our data. We don't typically pass through, in fact, it's usually bad practice, to pass all of our data through the network at once. We don't tend to do that. We split up the data, carve it all up, and we put it through in bits, basically, in these things called batches. And once we've passed through all of the batches from our data once, then we've completed an epoch. Okay, so in each iteration, so in each batch that we pass through, we pass our input data for that batch through the network, trying to predict our Y, our output, our in classification problem, that's our label, and this is known as a forward pass through the network. We then calculate the loss, the error that's predicted between the predicted and observed values of Y. So how far off the correct answer were we? And then we back propagate the loss throughout the network, the blame assignment, which bits caused it to be wrong, and then use the optimizer to update the weights. Now, the good news is that Keras, which is the API that you're going to be using that sits on top of TensorFlow. So TensorFlow is the neural network building framework that we're going to be using, developed by Google. I think the most widely used now in the world. If you just use raw TensorFlow is incredibly complex to use, but we use something that sits on top of TensorFlow called Keras, which basically allows mere mortals like us to be able to use TensorFlow, and it simplifies things so we can give it commands that we can understand. And Keras will do all this for us. We just specify we want a network that looks like this, these amount of layers, I want to use these loss functions, that optimizer, etc., etc. There is another alternative to TensorFlow known as PyTorch, which is also commonly used. Some people prefer PyTorch to TensorFlow, and with understandable reasons. So PyTorch, some would argue PyTorch is better for learning neural networks because the learning curve is steeper, but you have to know much more about the neural network because you have to do everything yourself, basically. So in this example, you have to do 2 and 3 manually. Or you have to run the steps manually, whereas Keras will do it for you. So I personally subscribe. So I get that school of thought. I think that ends up putting people off though a little bit. So Keras and TensorFlow, you just need to know it's doing this, but it will do this bit for you. Now, depending on what your problem is and the data you have, you might need a lot of epochs. 10 tends to be a good number to start with for no particular reason. You might need, if you've got a very big problem, you might need hundreds or even thousands of epochs to learn effectively. But remember, as ever with machine learning, be very careful about overfitting where you've learned things that are too specific to the training data and you've lost that generalizability that's so important for machine learning, and be careful of underfitting as well where we haven't learnt enough. Sammi, I'm just wondering, is it worth us taking? I'm conscious. Are people drained? Do you want a 10-minute break before we? Can some people indicate in the chat if you'd rather plow through for the next 10 minutes, or if you want a 10-minute break now and then we go? I don't want to drain people. If you can let me know what people's thoughts are. This will take about 10 minutes.
The consensus seems to be break. People would like a break.
I thought so. I'm just conscious this isn't exactly light stuff. So right, let's break for we'll break until 5:02. So 10:55 we'll come back. I've got a little bit more to talk about, and then you'll go off on your exercise. So yeah, okay. Let's break for 10. Stop talking, Dan. That's what I'm going to do. I'm going to stop talking. Hi everyone, welcome back. Okay, so hopefully that break's helped you just take a moment away from neural networks and let your some of that information settle in a moment. So just a little bit more to talk about before I set you off on this morning's exercise. Again, just to re-emphasize, don't worry if this is complex stuff. This is arguably the most complicated of all of the machine learning approaches. It is also arguably the most powerful. One thing I think you will see when you come to the exercise is that the good news is that by using Keras on top of TensorFlow, the code is actually quite straightforward. The important thing here is understanding not the mathematics, but because you don't need to code that, but actually what these broad concepts are. So a lot of the exercise is going to be getting your head around these concepts so that you feel a bit more confident sort of building your own neural networks. Okay, let me just share my screen again, and where did we get to? So here we are. So I talked about just before we went for the break. I talked about that we split our data into batches, and once all of those batches of our data have been fed through once, that represents an epoch. So let's just talk a little bit about batches here. So the reason we do that, we don't typically pass all of our data through at once. As I say, you might think, well, why don't we do that? Well, although if we did shunt all of our data through at once, we would train more quickly, the network would learn more quickly, we tend to get much worse performance because essentially the model is getting too much information at once. It's being overwhelmed, a bit like how you feel this morning with this lecture. It's too much information all in one go, and it means it isn't properly able to try and identify some of the nuances in that data. So in neural networks, we tend to split the data up into batches. So we chop our data up and we shunt it through the network a bit at a time. Now, The size of your batch is up to you as the modeler, and again is something else that you tend to play around with. There are no hard and fast rules, as with most things here. There is a popular opinion that was popularised by Yann LeCun, who's a French computer scientist, very big name in deep learning, that you shouldn't use batch sizes of greater than 32. Indeed, his quote is, training with large mini batches is bad for your health. More importantly, it's bad for your test error. Friends, don't let friends use mini batches larger than 32. But, that is itself not a hard and fast rule. Try things out. And indeed, when you come onto the exercise, you may find you don't do that. Don't stick to that rule initially. So see what works for you. And really is an art form here, more than anything. Now, if you're using a GPU, which I expect most of you aren't, but if you were to use one, of course, a GPU does thrive with larger batch sizes computationally, because of course they're designed to take on huge amounts of information all at once and process them simultaneously. But that doesn't still necessarily mean you should do it for the reasons we've discussed, that it can still overwhelm the learning, and you may get poorer performance because of it. Okay, so let's talk a little bit about overfitting. So we keep talking about overfitting in machine learning because it's a problem, and it is indeed a problem that will rear its head in neural networks too. So if we let a neural network train for long enough, i.e. enough epochs, enough full shunts of our data through the network, we will end up, I can always guarantee you will get excellent and possibly even 100% accuracy on your training data. But that typically means, unfortunately, that you have overfitted. And as we've seen before, that generally means it won't perform very well on data that it hasn't yet seen. And as with the other approaches we've looked at, we can usually tell that quite easily, because we see we've got really good performance on the training set, but actually much worse performance on the test set. We've got this gap between them. We also, if we plot our performance over time in a neural network, because we've got time as a factor in training with a neural network, because we're training over epochs, what you'll often find is that with an overfitted model, that the test set accuracy will start to go up, and then it'll gradually start reducing and then kind of plateau. That tends to be a sign of overfitting. So here we can see a model that has been overfitted. We've got this ended up with this amazing performance on the training set, and we were starting to improve things on the test set, but then it just started getting worse and worse, and then it plateaued. And there's actually quite a large gap between the training accuracy and the test set accuracy. What we can do, though, is take action, as we've seen with some of the other approaches like logistic regression and the tree-based models that Sammi looked at last week. We can do stuff to prevent overfitting, but particularly with a neural network, and generally speaking with most machine learning approaches, we tend to want to train a neural network first that has overfitted. And we do that deliberately because we know if our network has overfitted, then it has learned enough. It's learned too much. Okay, so we've avoided the problem of underfitting, where we haven't got, our model isn't complex enough. It hasn't learned enough of the nuance. We definitely haven't got that problem if we've overfitted. And overfitting, we can then take measures to then try and reduce the overfitting, so we get back to the point at which it's learnt not too much about the training data, but still sufficiently enough. So once we've got our model that we are confident is not underfitting, and we are confident because we've got it overfitting, and therefore we know it has learnt enough, just a bit too much, then we can try and tackle this overfitting problem. And we do that using something known as regularization, and you'll see regularization talked about in neural networks. It basically just means various approaches that can be used to try and tackle the overfitting problem. And this includes things like reducing the complexity of the model, reducing the amount of time that we allow the model to train. So in a neural network, we've got this concept that we train over time via epochs, and also adding something known as dropout. There's also something known as L1 and L2 regularization. I believe, from memory, Sammi mentioned about L1 L2 regularization last week. For neural networks, they don't tend to be used much anymore, so I'm not going to cover those for neural networks. It doesn't tend to be used so much in modern neural networks. But I will talk about some of these other approaches in turn. So first is to try and reduce the complexity of the model. As we've talked about before, a classification model that is overfitted is one that has come up with basically a line that is too adjusted to the nuances of our training set, and essentially it is too complicated. It has not captured the more generalizable division between those classes. So one way in which we can avoid the problem of overfitting is just to make our model simpler. That's a nice, easy approach that we can take to try and reduce the overfitting problem. Because by making the model simpler, we're reducing the complexity of this line that it comes up with. And in a neural network, that can mean things like reducing the number of hidden layers that you have, reducing the size of each layer in terms of how many neurons are on the hidden layers, etc., and all sorts of things that you can do to reduce the complexity of that network. We can also try reducing the training time in a neural network. Essentially, what we're trying to do is stop the neural network training before it gets to the point where it's starting to overfit. Now, we can either do that manually, so we could plot our accuracy on our training and test data over time, and see where we start to get what appears to be overfitting, and then stop the training manually there. Or we can use something known as a callback. A callback is just basically a function that runs repeatedly during a process. So in a neural network training, a callback is something that is run throughout the training process of the neural network. And there's a callback that you can use when you're building neural networks in TensorFlow called early stopping. And early stopping basically allows us to specify the minimum amount of change that we want to see in our performance metric between epochs, and also something known as patience, which is how long we're prepared to wait for things to improve. So basically what that allows us to do is automatically say, okay, I want to see this much improvement in test accuracy, and I'm prepared to wait for 10 epochs for that to happen. But if it doesn't happen, then actually we're starting to overfit and we need to stop. And that early stopping callback allows that to happen automatically, so it will do that analysis for you. And then we've also got this thing called dropout. Now, Sammi touched last week on some of the approaches you can use in tree-based models to try and effectively kind of switch off bits of your tree. Dropout works in a very similar way for a neural network. And basically what dropout does is during training or fitting, and only during training, it will randomly effectively switch off a bit of your network, and usually quite a bit of it. So it's typical to use between 20% and 50%. So up to half of your network is switched off during a particular epoch of training. Now, when I say it switches it off, what it's strictly speaking doing is you have, after each of your hidden layers, you have a dropout layer. And that dropout layer basically will, if dropout is enabled, will randomly switch off by setting some of these outputs coming out of these neurons. It does that by switching the weights to 0, and that effectively switches off that neuron's contribution. So if you can imagine between this layer here and this layer here, we've got a dropout layer that we can't see here, and that dropout layer on this epoch has decided to to effectively switch off this neuron, so that all of the connections that are coming out of that neuron, all of its weights are set to 0. So that neuron does not contribute anything during that training epoch to the next layer of the network. And similarly here, we can imagine a dropout layer just after it here, and it randomly switches off this neuron. So that doesn't have any say in the final output, that neuron's output. You might think, but that seems a bit crazy. Why would you do that? Turns out it's one of the most effective things you can do for reducing overfitting, because what it's effectively doing is it is stopping your network from becoming obsessed with something in there, because it can't become obsessed or too over-reliant on a particular aspect of your network, because at various points it will randomly get switched off. So it forces it to look at everything and not just become increasingly kind of obsessed with one part of your network, which might be really important for the training data, but not generalizable. So it kind of forces it to not become too over-reliant on various bits of your network and force it to look much more widely. And it's a very, very effective tool for trying to reduce overfitting in neural networks. Now, this dropout only takes place during training. So once you've then fitted your neural network, there is no dropout. So that when it then makes predictions on your test set, etc., all of the neurons are switched on. There are no unless it has learnt to set weights to 0, but not through dropout. There will be no official. The dropout layers will effectively not do anything at that point. I'm also going to mention something here which I touched on much earlier, where I said in that very simple example of a neuron, I said here are the numbers that are flowing through, but that's a vast simplification for a number of reasons. And I said one of the reasons is that the numbers don't look like that. So far we've been using these kind of simple numbers to try and get our heads around what each of these neurons are doing. In reality, it's a little bit more complicated than that. The numbers that are feeding through aren't numbers as we might understand them. In fact, they're shaped as something known as a tensor. And a tensor gives the name TensorFlow, gives it its name. A tensor is basically the shape that your data needs to be in. The numbers that are flowing through your network need to be in tensors, and it represents the shape that a neural network needs. A tensor is a pretty complex concept to understand, but for your purposes, you just need to think about it as basically a kind of generalization or an abstraction of the concept of a scalar or a vector. Scalars and vectors are themselves tensors, but you may remember from school that a scalar basically is a quantity that has magnitude but no direction. A vector has both scale and direction. Both of those are examples of tensors, but tensors can actually go into multi-dimensional space. And of course, multi-dimensional space is what we need for complex machine learning problems. Don't worry too much about that. You just need to know that the tensor is the shape that you need, and it's not just as simple as just chucking in some numbers. They have to be shaped in these tensors, and because they're shaped as tensors, we have to do things to get them out to the other side. You will see though that the Keras does a lot of the heavy lifting of that for you in terms of the code. But just be aware that that's what you do, because you will see bits in the code that you're going to look at this morning where it basically has to get it into the right shape. That's what we mean by it. Think of a tensor as being a kind of blob of numbers that the neural network needs it in that blob-like shape to be fed through your network. And as I've mentioned, up until more recent years, really, these kind of neural networks were not something that the average person would be able to build themselves. They were very much reserved for those mathematicians that did understand the complex mathematics behind them, or computer scientists that did sit in the lecture that I did and understand it. But the great news is that you do not need to be one of those people. It is much more accessible now to be able to use and build and train your own neural networks, because of these packages that have emerged, like TensorFlow, like PyTorch, that allow people to be able to do it without understanding all of the complex mathematics behind them. So you just need to understand more of the general concepts of, I understand broadly that backpropagation assigns blame across the network. I understand an optimizer is the thing that adjusts the weights to try and reduce loss, which is the error. That's the kind of level you need to understand, not here are the mathematics behind backpropagation, unless you really want to and you feel very mathematically inclined. So we're going to be using in the HSMA course and in the session, we use TensorFlow with the Keras API, which sits atop TensorFlow, which itself is pretty complicated and makes things a bit easier for us to interact with TensorFlow via Keras. And we can then issue Keras commands in Python, which allow us to, and hopefully you'll see the code this morning, doesn't look perhaps quite as imposing as you might think from all of this lecture. In fact, you might be pleasantly surprised by how straightforward the code looks. Okay, any questions that have cropped up, Sammi, in that little extra bit that we've done there?
So there was just some clarification around so when we were talking about batching, what was kind of like 32 in relation to. So I think the answer to that one is 32 is sort of 32 samples. For example, in the Titanic data set, that would be 32 rows of data at a time. And then the only thing that kind of came out of that was, does that mean that you'd have tens of thousands of batches for some very large data sets? And I think the answer there is yes, and that's part of why they do take so long to train. I think my understanding is that batches that are an even number are more computationally efficient, or possibly it's something to do with memory size. Or
That's
multiples
right.
of specifically of
Yeah.
16 maybe, but so that can help save a little bit, but it will just take time. The other one, so I think most of these have been answered, but I'll just draw attention to this one. So if we're using early stopping, are we not using our test data to choose which training set we use? So it's no longer effectively a true test set. Should we use something like a validation set there instead?
Yes, and I'm going to apologise in advance because, and I draw attention to this. I'll blame Mike because he's not here, and it's based on his workbook. The notebook you're going to be looking at this morning uses the test set as the validation set. That is bad practice in general. You shouldn't, because it should not have access for the reason we talked about before. What you should do is carve out three types of set from your data. You should have first a split between training and test, and then test shouldn't be anywhere near your training. And then from your training set, you can carve off a bit of your training set as your validation set. And then it's the validation set that you would then use to compare performance. And then only when you are happy that you think, okay, I have got my trained model, here is the finished product, you then go out and you use your test set, which is never seen before, and you say, and the performance of this is this. And that's your final answer. I'm flagging that up because you will see it'll, for simplicity in learning this, it will make the notebook a bit easier to understand. It is flagged up in the notebook as well. That is not what you normally do. You would normally carve off a validation set. When we come on to module 5, you will see examples of where you can, how you carve off this stuff. That's what you should do here if you were doing this for real as well. So the code will be the same, but just be aware that is bad practice. Not you should keep your test set well away from the training. Was that everything, Sammy?
Fantastic. I think so. Yep. Sorry. Just the other thing. Someone's just asked, is there a collab link? I've just posted those in the class tannoy now. There any examples of code in the course that does the three-way split of training, validation, and test? Off the top of my head, I'm not sure, but I can definitely add one of those for reference into our into the final session, where I think I do have a slide to talk about that. So there should be a code example coming up then.
There is in module
And
5, sorry, in natural language processing, where you use, when we get into sentiment analysis, you'll be using neural networks for words, and you'll be using test validation train splits. Sorry, yeah, train validation test splits, and it'll show you how to do that. So, and it's the same principle. So, yeah, that isn't. Apology. I would try to, Sammy. I wonder if you can put a note in our syllabus spreadsheet to correct that. Actually, I only kind of this has gradually evolved from Mike's materials, and there's things I'm still spotting, and obviously because we're just taking bits out of Mike's stuff in the Titanic, it does go into that more later, but obviously we're zooming into little bits, and we've zoomed into a bit there where he's just using not using a validation set at that point. Yeah, we will correct that for next year.
yeah, fantastic. Will do. I think that's everything that hasn't been answered in the chat. So good to go.
Okay, great. In which case, I think I've talked for far too long. So we're going to set you off into your groups now. Now, because we've overrun, what I'm going to suggest we do is we change the timing of this slightly. So I'm going to basically give you until just before 12:30. And I'm going to ask you to post, rather than come back and present, I'm going to ask you to post screenshots in your Slack channels that Sammy will judge. So basically what you're going to do, you're going to work and for the next hour and 10 now, in your groups. First of all, you're going to work on the notebook HSMA neural nets that's in the repository. Now, let me just bring up that notebook for you. This one here, HSMA neural nets. There's a lot of stuff here that summarizes some of the things and also adds in a few extra bits that we've talked about in the lecture. Now, I would strongly recommend that before you even get into the code, I would strongly recommend as a group what you need to do. One of you needs to share your screen. If you've got somebody with a faster computer than the rest of you, maybe get them to do it. It shouldn't matter too much for this. It's not I haven't given you anything massively complicated, but you may. It's not going to run as fast as mine probably, so just be aware of that. But I want you to read through this as a group. Lead through this and check, pause after each bit to make sure everybody is understanding these concepts, because this really is what you need to understand. Because when you get down here to the code, let me find it. Where is it? Here. That's the block of code where you write a function that builds a neural network. And there's not much in it. Okay, so you will see that actually most of this is trying to understand the concepts behind it. Once you understand the concepts, building neural networks becomes a bit more, as I say, of an art form where you're just saying, okay, I'm going to try it with 3 hidden layers, and I'm going to try 12 neurons per layer, and that kind of stuff. That's where you'll be doing a lot of your work. So use this as an opportunity as your peer support group to check to make sure everybody's understanding these concepts. So you're going to gradually work your way through that notebook. Once you're then happy, you've got everything working, and you've got the you follow through all the code examples, and you've run all the code. Your next task as a group is to go into the other notebook that you've been provided with, which is X1. And basically what this is going to do, it's going to load in that same stroke data you used back in the logistic regression one. And can't remember, Sam, if you used it for your one last week, but the stroke data that you've seen that predicts whether a stroke patient receives clot busting treatment or not, exactly the same as before, and that code cell there will load in that data and store it for you. And then you've got a series of prompts to basically try out a neural network on this problem. So you're going to build a neural network, and then once you build the neural network, you're going to get a baseline score. So it prompts you to use certain sort of baseline values. And then you're going to play around with that neural network and see if you can get better performance from it. and by better performance, I mean better performance on the test set. So we're looking at test set accuracy, and I'm going to ask each group to post a screenshot of their best performing configuration with a note on how they did that in their Slack channels. And then over lunch, and I'm going to ask Sammi to identify the best three or more for some PSG points. So there's some points up for grabs if you manage to get some decent performing models, decent performing neural networks out of this. Make sure you save your fitted models as the best ones as well, and don't forget to switch to your TF_HSMA environment that has been supplied to you via this repository. Okay, so I will open up the breakout rooms now, and we'll be floating around. But remember, the key thing you need to do first of all, get somebody sharing their screen and work your way through as a group, talking through the concepts that are in there. Make sure everybody understands these concepts. That's vital before you go on any further. Okay, let me stop sharing and